Hello, welcome to the On Semiconductor webcast. Today, we would like to discuss our power MOSFETs and especially the advanced thin ATPAK package, which has excellent thermal performance. It is intended for use in switching device applications. Currently, there's a great demand for low power consumption and energy-saving electronic products to meet and exceed the energy savings requirements from governmental and industry standards organizations. The power MOSFET has become the standard choice as the main switching device due to its low switching losses. Thinner and smaller electric devices are becoming more prevalent in consumer electronics. The power supply accounts for a large part of the electronic component blocks in terms of both space and weight. Because it is required for design engineers to improve the overall power supply efficiency, a reduction in power loss while allowing large load currents has become more important. Of course, the required mounting space and the weight always need to be reduced. Power MOSFETs offer excellent performance in high-speed switching, high breakdown voltage, high current, and low power loss. They're excellent in high-speed and high-frequency operations. Power MOSFETs are widely used in switching regulators such as AC-DC or DC-DC converters and motor controllers. Power MOSFETs consist of three electrodes: gate, source, and drain. Using a trench structure inside the silicon as the gate, the current path builds up between the source and the drain, upper and the lower regions respectively. If an N channel is located directly under the oxide film of the gate in an N-channel MOSFET, electrons are collected there, and in the opposite case for P-channel MOSFETs, where holes, which are an absence of electrons, are generated in the P-channel directly underneath the oxide film. The current flows vertically between the drain and the source. The trench structure makes integration easier and results in a lower on resistance, or RDS. Breakdown voltage between the drain and the source and on resistance are the two of the most important parameters. The breakdown voltage between drain and source refers to the maximum voltage you can apply between the drain and the source. You need to select the right breakdown voltage between the drain and the source according to the supply voltage and the required design margin. On resistance refers to the resistance to the current flowing from the drain to the source. On resistance and breakdown voltage between the drain and the source are usually in a trade-off relationship. In general, the higher the breakdown voltage, higher the on resistance becomes for devices with the same die size. When you select a power MOSFET, make sure that you select a device with both drain to source breakdown voltage and on resistance matching your application requirements. But before you select a power MOSFET for switching applications, you need to understand the following additional characteristics. There are several challenges you need to consider: switching speed, temperature, voltage, avalanche capacity, and package. Switching speed correlates to the total gate charge that needs to be charged or discharged in the gate drive circuit. It's denoted as QG. It is critical to choose whether you need to minimize the on resistance or to accommodate fast switching speed by keeping the gate charge under control when designing a MOSFET. For the development engineer of the application, it is important to choose the optimum MOSFET and trade off on resistance power loss versus switching power loss for the given application. The other challenge is to minimize temperature. In other words, engineers need to select a device that does not exceed a designated temperature when they design applications. Meanwhile, you need to make applications smaller and thinner to meet market demands. As package size gets smaller, the temperature inside of the device tends to get higher as it becomes more difficult to extract excess heat. This is a challenge for engineers to accomplish two contradictory design requirements. Next, power density refers to power per unit area or unit volume or unit weight. The allowable power loss of a power MOSFET is limited depending on a particular application. In a design, the power consumption needs to be below the allowable power loss. Avalanche capacity refers to the level of susceptibility when energy stored in an inductance is discharged into a power MOSFET. During the design, avalanche energy and avalanche current have to be taken into consideration. As for the package, there are two package types. A surface mounting package is used for portable devices such as smartphones and tablet PCs. A through-hole package is used for power supply and for industrial equipment. Each application has its own thermal resistance, and you need to select the package and device according to your application requirements. ON Semiconductor's cutting-edge ATPAK power MOSFET package has been designed to overcome the challenges mentioned earlier. One of the features of the ATPAK package is low height. Compared to the industry standard DPAK package size, the ATPAK reduces the height by 35% while maintaining the same footprint. From a cost standpoint, the cost of the ATPAK is nearly the same as the DPAK, but smaller and more efficient, making it a good replacement for your design considerations. We have also adopted clip bonding technology in order to minimize thermal resistance RTH, to minimize on resistance RDS on, and to increase current capability ID max. Formerly, we used wire bonding technology using gold, copper, or aluminum wires in order to connect each electrode on the silicon chip in the package. However, since each wire is relatively thin, it is difficult to allow higher load currents without excess losses. We've successfully reduced the on resistance and realized better thermal conduction by connecting each electrode directly with a copper clip, overcoming the above stated disadvantages. The structure of clip bonding technology uses a copper plate with a wide section area. This enables the increase of total full load current without concern for the fusing current that occurs in conventional wire bonding. In applications where the on resistance is required to be lower than 10 milliohms, the resistance in the wire, which is approximately a couple of milliohms, cannot be ignored. In the ATPAK package with clip bonding technology, by deploying a copper clip with a wider cross-section area compared to that of gold, copper, and aluminum, results in a drastic reduction in the electrical resistance in the source-to-drain paths to the external pins. The resulting reduction is on the order of 90% compared to gold wires and by 30% compared to aluminum wires. Besides, the advantage of the ATPAK, as we mentioned earlier, is that the package cost is about the same as that of the DPAK. Therefore, the ATPAK can be a great replacement for the current DPAK MOSFETs, but with better characteristics. We conducted a benchmark test between our ATPAK and the DPAK using the evaluation board shown on the slide. We measured the temperatures using thermograph equipment. We ignored the impact of the board on the heatsink since we mounted the ATPAK and the DPAK in the same position on the evaluation boards. The MOSFETs were both controlled to dissipate 1.44 watts and the temperatures were recorded. You can see that the surface temperature of the DPAK package reached 80 degrees Celsius, whereas the surface temperature of the ATPAK package reached only 74.8 degrees Celsius. This is a temperature difference of almost 5.2 degrees. If we estimate the junction temperature based on the thermal resistance, our calculation shows that the gap was approximately 6.2 degrees Celsius, which validates the test result. The table on the slide summarizes the test result. Power MOSFETs in the ATPAK package are used for a variety of end applications. Among these, there are DC-DC converters using low voltage and medium voltage MOSFETs, primary stage power supplies using high voltage MOSFETs, and secondary stage power supplies, various motor drivers, and multi-cell lithium-ion battery protection circuits using low voltage and medium voltage MOSFETs. ON Semiconductor offers a wide range of P-channel devices. We have the most diverse product portfolio in the market today. We also offer a wide range of N-channel power MOSFETs. Our portfolio allows you to select the MOSFETs based on breakdown voltage, on resistance, and gate voltage in order to find the optimum device matching your application needs. For more details regarding the complete portfolio of ON Semiconductor ATPAK MOSFETs, please contact your local ON Semiconductor sales representative or authorized distributor. For more information about the ON Semiconductor ATPAK Power MOSFET products, please visit us on the web at www.onsemi.com. Thank you very much.